computer. Find my files. I'm sorry about this. This is just one more YouTube video I have to make. I love technology. That's why I'm in this field. No, Zoom. Zoom. Go back to Zoom. What is the thingy? I say share screen is the magic word here. I am recording and PowerPoint. Okay. We need to bounce ahead. We've only got a few more slides to get through. Still nothing new from what we saw in, nothing new from what we saw in EE380. So we said this was in saturation, and we said this part of the current, which is big ID, the 1/2 Kn prime, W over L, VOV squared, VGS minus VT is just VOV squared, so I usually just throw that in, was 360 microamps. We want to calculate what the actual current is, taking into account channel length modulation. Well, all I do is I say, well, my new ID, and I'm going to call this, let me do this right, get my case right, little ID equals big ID times 1 plus lambda VDS. And my big ID was that part of the equation, so I'm not going to calculate it again. 360 micro times 1 plus, I'm given lambda's 0.1, and in this case, VDS is 1.3 minus 0 is 1.3 volts. I calculate the new lambda and the new current, and it comes out to be 406.8 microamps. Quite a difference. You're talking 10% difference in current. So yes, it matters. That can definitely affect an analog circuit, and it will affect the speed of your digital circuits. So again, the trick, figure out what this is. This is big ID, and little ID takes into account the channel length modulation. So another way we can model this is, since this is a line with a slope, we could take the slope of that line and figure out and use that to create a resistor that I'm going to add into my circuit model. So here's the equation, including the effect of VDS. If I take the derivative of that equation with respect to VDS, that should be everything cancels out, and then flip it over. So all this part right here is just ID. And I get the lambda, and then the VDS goes away. So my output resistance is the change in VDS with respect to ID, with VGS equals constant. You take that derivative, you get little RO is 1 over lambda ID. And this is an important enough effect in the transistor that it goes into the first order hand calculation model. Not even beyond what we do in SPICE, which is like Mentor Graphics or Multisim. So my model of the transistor for small signal looks like this. I have an AC VGS. This is the gate. This terminal must be the source. And what's left over is the drain. I have something we haven't talked about yet. I have a dependent current source. We talked about it in 280. It's some constant GM times VGS. And I put a resistor across here, little RO. It's not a physical resistor that resides inside the transistor. It is a linear model to make the equations work out, and it's modeling the slope of this line. It only exists in saturation. So it's not a physical resistor, it's a modeling resistor. People at issue like it. Okay. So if I have these transistors, what I do for this equation to calculate RO, I use big ID. I use the part of the equation that does not include the channel length modulation, because that'd be like doing it twice when I put the resistor in that model. Once I know big ID, in this case for this one it was 360 microamps, calculating RO is relatively trivial. RO is 1 over lambda ID, 1 over 0.1 times 360 micro. You're expecting answers in the kilo ohm range here, and 30, and that comes out to be 27.8 kilo ohms. Wait, is that right? Dr. Brower, you're confusing me. 30. 27.8 kilo ohms. Yeah, I don't know where you got that from. I'm going to ignore Dr. Brower for the moment. So yet another way of doing these curves, we did the ID-VDS family of curves. Looks like this. VDS, ID. This is where we get the curves that look like this. If I do a different sweep on the transistor, this is called a diode connected transistor. Well, we'll get to that later. Basically, the VDS equals VGS because VD equals VS. Those two are tied together. So they're constant, and if that's true, is VDS greater than VGS minus VT? VDS has to equals VD equals VG, which means VDS equals VGS, which means this, and that's a negative sign, and VT for an NMOS is positive, so that equation always has to be true. Right here, if we have VGS less than VT, we're in cutoff. And right here, we're going directly into saturation. There's no triode in this curve because VDS is always greater than VGS minus VT. We look at the current equation in saturation. ID is Kn prime over 2 W over L VOV squared, which is usually the way I write it because it's shorter. That's just VOV is just VGS minus VT. What we have here is we have a curve as VGS increases. This is going to be parabolic because I've got this squared term in there. So this is just yet another way we can measure transistors. And my little curve tracer I had at JPL would measure these curves and would measure these curves. Because that's what I was doing in my full-blown semiconductor physics geek days. PMOS is the same as NMOS except reverse. You just need some practice. I usually don't put PMOS transistors on 280 exams. You will get PMOS transistors on 380 exams. For an NMOS transistor, oh, let me draw the picture. Let's do an M. Let's do this. You had to do this on the homework. N plus. Don't get excited drawing. I'm almost done. P sub. So here's the M and the gate. This is the NMOS. And people, especially I know Micron, this is like one of their favorite interview questions until they found out it was one of the test questions. Then they got really tricky. So this is P plus, this is an N well. Let's look for PN junction diodes here. Now here is the body. The body, if you look here, right? Let's change colors. If you look right here, you've got an N diffusion right next to a P diffusion. You have a PN junction right along this boundary. Now, one thing you have to do in order to make sure you do not wreak havoc in your circuit is you never want to forward bias that PN junction. If you do, you're going to have huge amounts of currents flowing through here in places where you don't want currents to flow. So to keep this PN junction back biased, this P substrate has to be the lowest voltage in the circuit, usually tied to ground. So then this is the body tie. It's tied directly into the substrate. So usually I tie almost always, I tie the body of NMOS to ground. NMOS to the lowest V in the circuit. This will save you a lot of time in the lab. And so we're going to call that ground. Digital circuits, it's usually ground. Now, if I go over to the PMOS device over here, it's built in an N well. So now the body is tied to that N place. I have another PN junction right here. Now I want to make sure the N well is always the highest voltage in the circuit, so I don't forward bias these PN junctions and wreak havoc on my circuit. So now I'm going to tie the body here to VDD. So the body, put stars next to this, because I'll have to repeat this. I'll have to repeat it anyways. The body on the PMOS goes to the highest voltage in my circuit, which is usually VDD. And in the lab, we use the 4-terminal transistors and Mentor graphics. So you have to actually physically draw wires to those bodies and make sure the NMOS bodies are all tied to ground, the PMOS bodies are all tied to VDD, otherwise your circuit will not work. The drain current equations are exactly the same, but now the current's flowing in the other direction. It's coming out of the drain. So we usually draw these upside down so I can put the higher V's on top, because the source has the higher voltage, and that just saves me some things. The operating region, we've gone through the algorithm already and I'm running out of time. And the bias conditions, if you follow these little algorithms, write them down on your note sheet, it will help you, especially if you can find the body, the drain, the source, and the gate. For PMOS, just remember the gate's here, source goes up, or the source is where the little arrow is, and the drain goes down. And you could figure out all those operating regions. And I am done. If you have any questions, I can stick around for a few minutes. And then I get to go happily make YouTube videos. I'll do that tomorrow. Let me do roll one more time. Danielle, are you here? Or Sigwy? Pink. Okay.
Danielle's here.
Oh, yay. Okay, so Sigwy, it's like the middle of the night in China, so he usually watches the videos. So he doesn't have to get up at 2 o'clock in the morning and listen to me talk. So that's about it. Any questions? I will be in my office hours tomorrow by Zoom, or I will be physically in my office if you're brave. And because this is what I do. I can't work at home. Home needs to be home, and it needs to be away from this stuff. Otherwise, I work all the time. So I keep my home separate. But I'm in an empty office, so it's not very contagious. Right now, there's 4 people in the building. Okay. I will see you guys on Thursday. This class can be fun. This is a really interesting field. Once you get the basics down, there's a lot of jobs out there. TSMC, they're building a 5 nanometer fab, state of the art, down in Phoenix. For Tron, Dr. Cambeau is talking about getting partnerships with them and building business relationships with them which will help you guys, because it'll help you guys get jobs down there. And it'll mean that all the other fabs down in Phoenix are going to have openings when everybody goes to TSMC. And so there's just going to be more jobs all around. It's a big deal for Arizona, especially for Arizona electrical engineers who like the stuff that I teach. Okay, I will see you guys later. I'll expect your video in 4 or 5 parts next tomorrow, but I will see you. Okay, bye.
Thank you.
Okay, bye.
Thank you, Miss Julie.
Okay, I'll see you, Gabe.
Julie, so
Yes.
do we just have to turn in the homework tonight?
It was due at 4 o'clock. It was due an hour ago.
Oh, I thought you said that we were going to discuss it in class.
Well, we did discuss it in class, but it was still due an hour ago. You want me to give you some more time?
Yeah, I just wanted to finish that one problem.
I will give you until midnight,
All
because
right.
that's when the solution goes live.
Okay, cool.
Okay, I'll see you. Okay, bye.
Bye.
Okay, what are we doing? No, 380, 280, 380. $380. Okay, and it sounds like. Other parts. What's up with this? Just, I'd be surprised. Close. Just stop. Go away, Mr. Zoo. I'm still. Oh no, I'm still recording. Bloopers from Julie's. Just stop. Ed, go away.